Hi guys, today we will discuss about complex number. Complex number is another kinds of number which we will describe over here. Till now, like till quadratic equation, APGP, or whatever problems till you have learned your 10th class, you people are aware of simple number. Simple number means you will say, boss, I have learned about root over 5. So root over 5 is a simple number. I will say yes, that is a simple number. That is not a complex number. I cannot say that is a simple number, but that is not a complex number. But here we will discuss one different types of number, and that number we will denote as a complex number. So this complex number exercise is a very important for your West Bengal joint as well as your board examination, because complex numbers carries good marks for your examination, as well as it is generally combined with APGP and quadratic equation as well as trigonometry. So it will give you some good marks, and the problems and solutions of complex numbers are not that much complex. Rather, if you know the theorem or if you know the shortcut rules, then the problems and solution you can be able to make quite easy. So complex number is a coding paper, so you have to understand the concept of complex number. So let's start. First, let's start with the syllabus of West Bengal Joint Entrance. Whatever is there is the syllabus. The syllabus is mentioning about definition and properties of complex number, complex conjugate, triangle inequality, square root of complex number, cube roots of unity, De Moivre's theorem and its elementary application, solution of quadratic equation in complex number system. When we will discuss at that time, you will understand like why we are emphasizing on quadratic equation, because whenever you will solve the quadratic equation problem, at that time only you will encounter the complex number. So that is the quadratic equation and complex numbers are quite they are having relations basically. So you can understand like complex number has come from the concept of quadratic equation. So that's all. Let's go to the definition and properties of complex number. The history of complex number goes back to ancient Greeks, because you know there are very lots of Greek mathematician who has put the lots of rules of ancient mathematics, and lots of today's mathematics theorem and rules, all these things has come from Greeks. So our first concept was that no number existed that satisfies x square equal to minus 1. When x square equal to minus 1, you can write that x equal to, what will be x? X equal to root over of minus 1. Now, do we know what is root over of minus 1? So, as we don't know what is root over of minus 1, from this place, the complex number concept will come. Let's take one example. Diophantus, that is about 275 AD, attempted to solve one very good problem, that is the find the sides of a right angle triangle of perimeter 12 units and area 7 square units. This is a very simple problem. We have deduced these things into class in our class 8 or 9 or 10. That is, for a right angle triangle, we know that hypotenuse square equal to base square plus perpendicular square, or we have resolved many problems with right angle triangle. So let us take our right angle triangle exercise. That is, let's say ABC is a triangle where AB is the base and AC is the perpendicular. So I can write the hypotenuse is root over of x square plus h square, because this is a right angle triangle. So so we are considering AB equal to x, that is the base equal to x, and AC, the height, is denoted as h. So the area of the right angle triangle, area we know that half of base into perpendicular, so half of x into h, and the perimeter is x plus h, AB plus AC plus BC, so it means x plus h plus BC. BC means root over of x square plus y square, that is because of Pythagoras theorem. So this is the simple things. Now from here we can reduce to 6x square minus 43x plus 84 equal to 0. Why? Because we have already known that perimeter equal to 12 and area equal to 7. So I am just putting those things into the problem, and we come to know that the final expression is coming as 6x square minus 43x plus 84 when perimeter equal to 12 and area equal to 7. But do this quadratic equation have real solutions? If you do, then you will be understand no. One similar problem was posed by Cardan in 1545. He tried to solve the problem of finding two numbers a and b whose sum is 10 and whose product is 40. So let's say there are two numbers, one is a, one is b. So a plus b equal to 10 because the sum is 10 and product is 40. Product is 40 means a dot b equal to 40. Now from here, if I eliminating b, if I want to find out the roots of the value of a or b, so eliminating b from the first equation, we can get 10 minus a equal to 40. Fine. Now because the product is 40, so a into, in the second equation if I put a into b, b means 10 minus a, so a into 10 minus a equal to 40, or a square minus 10a plus 40 equal to 0. Solving this quadratic equation gives a equal to, you know, quadratic equation formula, minus b plus minus root over b square minus 4ac by 2a. So 2 into 10 plus minus root over minus 60, so this is the coming as 5 plus minus root over minus 15. So this means this is the root. So one solution is 5 plus root over minus 15 and one solution is 5 minus root over minus 15. So this shows that there are no real solution because root over of minus 15 is not a real number. But if it is agreed to continue using the number, so there will be two number, one is a equal to 5 plus root over minus 15 and another will be b equal to 5 minus root over of minus 15. So that the equation 1 and 2 are satisfied. So these are solution of the original problem, but they are not real numbers. Surprisingly, it was not until the 19th century that these such solutions were fully understood. The square root of minus 1, which is happening in the above expressions, are denoted by I, so that I equal to root over of minus 1. So a equal to, I can write a equal to 5 plus 15i, because root over of minus 1 equal to, I have mentioned that as I, and b equal to 5 minus 15i. So these are the examples of complex number. So whenever anything which is having a root over minus 1, that number we can directly consider as complex number. So that's all about complex number, a very short definition of complex number. I am not deducing much because I know that time is money and unnecessary. I don't want to speak much. Rather, let's go, we have to go to the problem and solution, because in joint entrance the problems and solution will come. The definition and concept are just preliminary idea so that you can solve the problems and so that you can solve the problems. Okay. In the next we will go to one example, that is solve if possible the following quadratic equation by factorizing or by using the quadratic formula, whatever your wish. X square minus 2x plus 2 equal to 0. So using the quadratic formula, I can get x equal to minus b plus minus root over b square minus 4ac by 2a. So if I just put b, a and c from the by comparing with ax square plus bx plus c equal to 0, it becomes minus of minus 2 plus minus root over minus 2 whole square minus 4 into 1 into 2 divided by 2a. A is 1, so 4 plus minus root over of 4 minus 8 divided by 2 into 1. So that means the the discriminant is coming root over of minus 4. Root over of minus 4 means root over of 4 into minus 1. So that is root over of 2 square into root over of minus 1. So 2 root over minus 1, it means 2i. As I have already discussed, the root over of minus 1 equal to I. So the solution becomes x equal to 2 plus minus 2i, right? 2. Now it becomes x equal to 1 plus minus of I, because 2 I am cutting down from everywhere. So one solution is 1 plus I and another solution is 1 minus I. So a number of the form a plus ib, where a and b are real and I equal to root over minus 1 are defined to be a complex number. So this is the simplest definition I have ever seen. That is, a number of the form a plus ib, where a and b are real numbers and I equal to root over minus 1 are defined to be a complex number. The real term not containing I is called the real part of the complex number. So a is the real part of the complex number, and the real b is also a real number, but I is a imaginary number. So the coefficient of I is called the imaginary part. So 2 plus I 3 minus 1 plus I root 3 comma 4 plus 4 plus I of minus 1 by 11, all are complex numbers. See, the terms which are having one I associated with this, that is called a complex number. Complex number is denoted by Z everywhere, and two complex numbers Z1 equal to a plus ib and Z2 equal to c plus id are equal if a equal to c and b equal to d. If for the two complex number both the real parts are together, like real parts and imaginary part, coefficient of imaginary parts are equal, at that time the complex numbers are called a equal complex number. So these are few these are the, now we will go through some of the properties of complex number. First property, that is sum of two complex number is a complex number, and we will define difference of two complex number is a complex number. Next we will define multiplication of two complex numbers is a complex number, as well as we will define division of two complex number is a complex number. So let's go to a short proof of these things. First one is sum of two complex numbers is a complex number. Let us take two complex number. One is Z1 equal to a plus ib and second one is Z2 equal to c plus id, and then the sum Z1 plus Z2 is defined as follows. I am just summing up Z1 plus Z2. So it means a plus c plus I of b plus d. I am just taking the I portions separate and the portions which is not having I, that is the real portions, which is having separate. A plus c, that is one number, so I am denoting that as a capital A, and b plus d is also a real number, so I am putting this as a capital B, and I is always there, so Z equal to a plus ib. Again a plus ib, if any number is in the form of a plus ib, I can tell that that is a complex number. So it is proved that sum of two complex number is a complex number. Next, go to the difference of two complex number is a complex number. It is on the same way we will deduce. Z1 I have put as a plus b ib, and Z2 I have put as c plus id. So if I take the difference of Z1 minus Z2, then it becomes a minus c plus I of b minus d. In the upper part it was all plus, and in the lower part it is just minus. So a minus c is a real number, so I can put that as a capital A, and b minus d is a real number, so I can put as a capital B. So it is becoming Z equal to capital A plus I capital B. So it means it is in the form of a plus ib, so I can tell that this is a complex number. Next one is multiplication of two complex number is a complex number. How? I will take the same example, Z1 equal to a plus ib and Z2 equal to c plus id. Now I will try to do the product of Z1 and Z2. Let's see how the product becomes. Z1 into Z2 equal to A plus IB into C plus ID. It becomes AC, then AID, then IB into C, then I square B into D. I know I square equal to minus 1, so AC minus BD. I am taking all the part of the expressions which are not having I in in one place. So AC minus BD plus I of AD plus BC. So I see here also two terms are coming. One is with real parts, another one is with I part. So AC minus BD I can take this as a capital A, and AD plus BC I can take as a capital B. So the expression becomes A plus IB, and that is also a complex number. So I have proved multiplication of two complex numbers is also a complex number. Let's go to the division now. So division of two complex number is a complex number. Let us take the same example. Z1 equal to A plus IB and Z2 equal to C plus ID, where Z2 not equal to 0, because the denominator of a division, if can be 0, then the division cannot be possible. So let's take how Z1 by Z2 is looking like. So Z1 by Z2 equal to A plus IB divided by C plus ID. I am just multiplying this expression A plus IB by C plus ID into C minus ID into both numerator and denominator. Okay, why I have done this? Because I have to prove something, so that is the reason. If I multiply the numerator, it becomes AC minus IAD plus IBC minus I square BD, and in the denominator it becomes C plus ID into C minus ID, that means A plus B into A minus B, that is A square minus B square. So it becomes C square minus I square D square. From here, from the numerator portion I am writing the terms which are with not with I. So AC and I square equal to minus 1, so this minus becomes plus, so plus BD plus I of BC minus AD, and the denominator becomes C square minus I square D square. I square equal to minus 1, so minus 1 and minus, that is plus, so C square plus D square. This means if I divide these things, AC plus BD divided by C square plus D square plus I of BC minus AD divided by C square plus D square. Here also I can see now one term is with I and one term is without I. So the first term, if I consider as capital A, that is a real number, and the second term if I consider as I of capital B is a real number, then we can see that this particular expression has also in the form of A plus IB. So this is a complex number. So these are the four properties of complex number. There are many other properties of complex numbers which we are not discussing over here, but in the problems whenever we will get, we will automatically deduce these things. But these four are a basic thumb rule through which different formulas will come. For today's lesson, next we will go through some more concept of complex numbers, like the modulus, the argument, the polar coordinates of complex number, those types of things, and then we will go to the problems and solutions. Thank you. Thanks for watching my video. If you like, please click on the like button in YouTube and subscribe me so that this video can be reached to a wider audience. Thank you. Have a good day.